I'm the Global Technical Promotion Manager functioning in a commercial capacity since April of this year. Prior to this, I was responsible for the R&D activities for about 2 years. And prior to that, I was responsible for new product introduction as part of the Process Technology Group, Analytical Development, and Regulatory Affairs. So today I'm going to be talking about 3 main topics. I'm going to give you a brief introduction about the Fujifilm Imaging Colorants and our heritage and our perspective and how we have gained it. Then I'm going to talk about a concept called life of a drop. And I will use that concept to then highlight some of the benefits of the reactive dispersant technology, which is a colorant technology that we have developed. Just out of curiosity, how many people are ink formulators and ink manufacturers within the audience? And how many are specifically working with water-based inks? Okay, thank you. So, good. So starting with the introduction of FFIC, this is the whole group of the Fujifilm with quite a bit of activity in printing market as part of the Fuji Xerox joint venture. There are some inkjet machines. We actually supply the dye-based inks and pigment-based inks into those machines. On the Fujifilm side, there is quite a kind of diversified portfolio with healthcare, biotechnology, cosmetics, functional products, chemicals, recording media, and of course the film and the cameras, which is the heritage of the Fujifilm. We are within the graphics system here. And if you zoom in, you'll see the 3 Fujifilm companies within the graphics system, all under the same umbrella. Fujifilm Dymatics obviously is the printhead company, and then there is the 2 ink companies, Fujifilm Specialty, covering UV inks, and Fujifilm Imaging Colorants, FFIC, covering the water-based inks. It's quite an interesting relationship that we have. There's not a lot of companies that have all of these capabilities under the one umbrella here. But we also have external relationships. Everybody asks us if we exclusively make ink for Dymatics printheads, and we do make inks for Fujifilm Dymatics heads, but also for a number of other printheads as well. Just as Dymatics has a number of ink partners, we have a number of printhead partners as well. These 3 companies are actually supported by Fujifilm R&D laboratories in Japan. There's about 2,000-3,000 scientists that can support us for I'm sorry about this. For producing new molecules, new formulations, and new systems. So that's in addition to our local R&D activities, which gives us a lot of capabilities for new products. And zooming into the FFIC portion of this, I'm going to give you a little bit of background about our heritage and where we come from. We initially actually were an ICI company. And we got engaged in the market in the early 1980s. Was actually interesting because the customers came to us. These are the very early pioneers in the inkjet who have developed the inkjet technology, have a very precise way of delivering liquids onto a substrate with all the chemicals to modify surface tension, viscosity, but they had no tolerance. So at this point, they were coming up with the first generation ink that they were using in the printers, and the colorants that were available at the time that were water-soluble and safe were mostly food colorants and also textile colorants. And ICI had a very large portfolio of textile colorants for coloring leathers and paper with direct dyes, reactive dyes, also acid dyes. And those basically became the first generation colorants that went into the first generation printers. And it's very interesting, the industry, it goes in cycles, and you can see that all of those dyes are now coming back as the textile digital printing is taking off, and it's actually being used for the proper application. So one thing that really distinguished the dyes that were used for inkjet versus the textile application was the really high purity. So we developed a number of methods for removing all the organic impurities, inorganic impurities down to sub-ppm levels. And that gave us the kind of inkjet grade dyes. And at this point, ICI had basically a very prosperous business with a lot of potential. So they added an R&D engine to actually develop specific dyes for inkjet applications. One of the shortfalls of the very first generation of the dyes was the poor water fastness because they were highly water soluble. So we came up with the second generation dyes, which had very good water fastness, almost close to approaching kind of pigment type behavior. And that was a breakthrough at the time. And after that, additional targets were added for developing photo-grade dyes and ozone-fast and light-fast dyes and so forth. And Avicii really became the leading global supplier of all these dyes into inkjet. And in 2006, Fujifilm purchased us, where we added a full line of products for photo-grade dyes that Fujifilm owned at the time. So we expanded our portfolio significantly. We became part of Fujifilm family. That also made us the biggest competitor of our biggest customers, so we had to do a lot of hand-holding and so forth. But it put us in a very interesting position within Fujifilm. And at that point, we also added pigment dispersion, because that was very important for the future of the business, which I will be talking about in a bit. As far as locations, we have 2 centers of excellence, one in UK, where we make all of the colorants, and also one in US, where we do all of the colorant purification and ink formulation activities. We have the largest capacity for making water-based inks. Our mature products typically are made at around 20,000 liter batch size. Very high quality structure, and a number of capabilities for dye purification. Right along the side, the manufacturing activities, we also have our own R&D activities, quite an impressive lab with a lot of competent and experienced staff. We also have scientists from Japan who work along the side with our scientists, and we get a lot of funding, local as well as from Japan. So we have quite a bit of state-of-the-art equipment that really allows us to do a lot of development. In Scotland, we have also a lot of sophisticated equipment for dye synthesis and also dispersion manufacturing. And these are equipment that were added to be able to make the Fuji photo dye products, basically. So quite an extensive capability at Grangemouth. And, of course, also development activities. Again, development activities for inventing new molecules, new polymers, and new dispersions, with all of the infrastructure for testing and development that goes along. Again, we have quite a bit of support from Japan as well, with scientists and collaboration with the R&D labs in Tokyo. So now I'm going to talk a little bit about this life of an inkjet drop concept. This is something that we developed in the 90s with the advent of high-speed cameras. It really opened up a whole new universe of information that we could tap into and really understand what happens after the drop formation and jetting. In particular, with regard to substrate interactions and understanding what happens with the ink once it hits the substrate and all of the subsequent steps. It's quite a simple but very powerful concept. You basically follow the drop through its entire life cycle, and you study and characterize every transformation step as you go along. So what is a transformation step? It's basically any type of change. It could be a physical change or a chemical change that happens, for example, during the drying of ink on paper. It could be a change in environment. You could be looking at a droplet as it's dislodged from the printhead or just before it hits the substrate. We heard a number of presentations yesterday about electrostatic forces, about turbulent flow, about deceleration of the speed of the droplet. So there's quite a bit of phenomena here that you can actually study. What's really key is to identify every transformation and set the boundaries so you know exactly what system you're studying and characterizing. One of the examples here that we used this technique for very early on was understanding the dry time of ink on substrate, on absorbing substrate. And these were systems that didn't have any drying or any heat built into the printers. So everything is happening at ambient conditions. And again, we weren't as much focused on jetting, but really on what happens once the ink arrives on the substrate. And there's a number of things you can, if you can actually model it, you can come up with all the different mechanisms of what happens. And there's quite a bit of evaporation into the environment. There's some absorbing of water into your substrate and kind of lateral diffusion of the ink. And if you look at this carefully, you quickly realize that it's basically physically impossible to evaporate all of the water and get really dry effect. So what you need to do is to come up with what will give you a dry effect while you still have quite a bit of water around. And being able to follow the life of a drop, you can actually use that to screen a number of different polymers and understand which polymer will give you the best effect within that 0 to 5 seconds where you will be handling the print and you want to make sure there is no transfer. So it was quite successful for us to be able to come up with the right technology to deliver that drying behavior. The other example where we use this as an R&D tool was studying the Bullseye Effect, where we use a hybrid system of dyes and pigments. And you can only do this with dyes that have very low water solubility, like the second generation dyes that I was talking about earlier. And what you'll see is if you only have a pigment-based ink, and if you're kind of looking from an aerial view, once the drop arrives on the substrate, you get some diffusion of the ink until the entire colorant precipitates and you get to a nearly dry condition. And that phenomenon is called drop gain. And you have a certain behavior for pigments, but if you add a little bit of dye, you actually get a very interesting behavior. Now you have two different moving fronts at different decelerating rates. So the pigment will travel slowly, the dye will travel faster and further. And if you look at the prints under the microscope, you can see all these bullseyes. And that little bit of dye that you add gives you a really big effect as far as filling the white space and also boosting the chroma. So that was another example, and you can see you have a physical phenomenon here, so engineers and mathematicians can have a lot of fun with modeling these things and using it to actually optimize your system. So we had a lot of success with this, and we decided to extend it for other applications. For regulatory purposes, you have to track the path of your ink and understand where it ends up. So that's what we did, looking at post-drop, where you look at the print, where the print will end up, where the chemicals will end up, and you can do your hazard assessment. And conversely, you can also, instead of moving forwards, you can move backwards and look at ink before drop formation, basically in the bulk state, and further back to the raw material. So you can map out the entire life of the inkjet drop before it's even formed. And now you have basically your entire supply chain, and you can use that to start looking at some of your quality assessment for your product. So when you look at those transformations, you can further break it down and look at what happens to your raw material during transport, packaging, warehousing, your QA inspection. And then ink manufacture, there's a whole slew of activities here for developing the process, all of your specs, the packaging and transport, shelf life of a product, and then eventually going through the print head when you add a whole new dimension as far as compatibility, jetting, and printing. You can also look at your value chain. As the value of the product keeps going up, you want to make sure that you have all of the testing front-loaded, and you basically make sure that the product going out the door is really fit for use because this supply chain can actually be as long as 1 to 2 years sometimes. And you don't want to have any issues with product that's already on the field. So it also proved to be quite a useful tool for quality assessment. The best time for doing that, for building that whole structure is when you transfer a product from R&D into production. And ideally, you want to have all of the function present. You basically lock everybody in a room for a day or two, and you go through the entire supply chain. And it's very powerful because you have R&D function, you have production function, people can ask questions, and there's a lot of communication back and forth. And you really add a lot of different dimensions. So if I am an R&D person, I'm interested in selecting a surfactant, and I'm looking at fluorosurfactants. I know I can add a small amount and get a big effect. But I also know that it's not going to help me with my dynamic surface tension as much as it does with static. So I need to have 2 different surfactants. So those are the things that I'm going to be interested in as far as the ratio of the surfactants and what's going to give me the best effect. Within the production, you will be interested to know what the molecular weight distribution is if the surfactant will go through a stratification. If I take material from the top or the bottom of a container, am I going to get different surface tensions? So you're really focused on process and handling the raw material. From a purchasing point of view, I'm interested if there is 3 different sources, I can get reasonable security of supply and pricing. So it really adds a lot of different dimensions, and you get a really comprehensive package as a result of that. And when you do this, you also have to do it twice. Once doing a temporal analysis and a second time doing a spatial analysis. And basically, you follow the life of a drop from time 0 to the end of the life and track it back to the beginning of its life. And you also do it with regard to spatial and location of the drop. The reason you do this, does anybody know why you have to do it twice to get a comprehensive view of things? If you think of the temporal analysis, temporal analysis, if you make ink and you have it in storage, it's not moving, but the time still, the clock is still ticking. So you need to be concerned about shelf life and chemical stability. But also from a spatial point of view, sometimes within a very short amount of time, a lot of steps and a lot of chemical reactions and physical phenomena happen. So you need to be able to model that, and an example of that was when we were looking at the Bullseye Effect, for example. So if you do it temporal and spatial, you get a really comprehensive package and a very good picture. So using that, you can get a very systematic and comprehensive tool within a multidisciplinary scope. It's very useful for building your failure mode and effect analysis for your product and also all the contingencies. That helps you to build your manufacturing plan so you can engineer out all of the failure modes. And also continuous improvement for cost down, where you can go back to your cost sensitive points and reduce the price or the cost of your product. And also, if you have any issues, it's very powerful for your root cause analysis. You basically have your fishbone diagram already done up front so that you can use. So now I'm going to change gear, talk a little bit about reactive dispersants, the colorant technology, and then use the life of a drop to highlight some of the benefits of that technology. So as I mentioned, in 2006, we decided to add reactive dispersant colorants to our portfolio of products. And we looked at all the available technologies, with polymer dispersants being one option. It's a very simple, elegant process, but it does have some issues with desorption of the polymers because that's a reversible process. If you look at the other technologies, encapsulation is also a very good process, but it's quite complex. You need to go through a number of polymer precipitations and number of steps. So it makes it quite complex process. Functionalized pigment, that's also quite a good technology where you actually react a polymer directly onto the surface of your pigment. But you need to understand the surface that you're reacting onto, and sometimes you have to build up that chemistry in several steps. And every time you do a step of chemistry, you're also having some byproducts and impurities that you need to clean up. So you may end up with 10 or 12 steps that will basically inherently make your product a bit complicated and not very cost efficient. So going back to the polymer dispersants, as I said, this is quite a simple, elegant technology, but it has one single flaw, which is the absorption is reversible. So if you're using organic solvents and aggressive surfactants, you can start losing your polymer. Now, if you can address that one flaw, you have a really good technology which is actually superior to the other incumbents. And that's exactly what we did. We decided to add reactive sites to the polymers where we can actually do cross-linking of those polymers and fix them in place. And these are permanent covalent bonds. So once you form them, you're not going to be able to break them anymore. And what's really important to distinguish between this technology and functionalized pigments is that the chemistry here is happening between polymer and polymer moieties. There is no reaction with the pigment itself. So it's completely independent of the particle that's inside of this polymer network. And that's very powerful. So now you have a very simple, elegant process. It's basically 4 steps by adding your dispersants to the milled pigment, adding water and dispersing it, cooking it for a number of hours to get the cross-linking to completion, and removing any residual buffer and impurities, and that's basically it. You have your product. So if you think about all the different attributes that we just discussed for reactive dispersants, you can then take this back and put it inside the life of a drop and look at all of the different benefits that you get at every main transformation point. And the nice thing about that is that if you go through those steps, you know, pre-ink, ink, going through print head and the final product, which is your print, because it's sequential and it's temporal and spatial put together, you actually get a really nice cause and effect relationship where the effect from one transformation step becomes the cause of the next one. And you have a really nice interrelationship. So just kind of magnifying that and looking at it one by one. At the pre-ink step, as we mentioned, the chemistry is really pigment independent. So you have a lot of flexibility as far as the polymer design is concerned. And you can use the same design for all of the different colors that you have. So there's good uniformity of the polymer design that you can do for K, C, and Y, red, blue, and so forth. It's a very simple and elegant process, so it's quite cost effective. There's only 4 steps, so you're not adding a lot of byproducts and impurities that you have to remove later. And the cross-linking is very, very important here. That really gives you excellent stability that at this stage gives you a really good shelf life for your dispersion. And of course, because you have good control of all of the conditions, you have control of particle size, of the physicals, pH, viscosity, surface tension, and strength. You have very good, consistent quality. One of the steps that I mentioned, the cross-linking, it goes through a high temperature cycle, so that sterilizes your product and it makes it bacteria-free. So again, that adds to the long shelf life of your product as well as the reliability of your product down the road. Moving on to the ink. Again, cross-linking translates to high stability. High stability allows you to have a very wide formulation window. And you can add a lot of different solvents, different surfactants that you typically can't use with other technologies. And that allows you to have also very good shelf life for your ink as well, at high temperature as well as ambient temperature. Because of the good control of the physicals, we can also produce a product at different strengths. So we have a 15% product as well as a 20% product. And that, as an ink formulator, you know that's a big benefit because you can add additional material because there is less water. So having a 20% strength product is a big plus. And of course, the polymer uniformity allows you to basically use the same vehicle for all of the colors. You don't have to change the ink formulation as you go from one color to the other. So that's also another big benefit. Once you get to your printhead, the low impurities, they give you really good compatibility with a wide range of different printheads. The low impurities also translate into low corrosion and long printhead lifetime, and these printheads used in industrial applications are quite expensive. So that's a very important benefit that you can get. Consistent physicals that will give you a very good consistent drop formation and jetting and high reliability. And wide formulation window allows you to have highly volatile inks that are suitable for high-speed printing. And that also is a huge benefit. When you get down to the actual print, you have a lot of benefits there again as far as the white gamut. You can use the same technology for 6 colors. You can also add orange, violets, all the different possible colors using the same technology. And the wide formulation window allows you to formulate ink that can work on difficult substrates, cellulosic substrate, paper, PVC, polyethylene, and so forth. So that's a big benefit as well. And of course, the polymer design gives you very good durability as far as the choice of the polymer that you use and some of the residual polymer that's in the dispersion as well. So all of those attributes and all of those benefits really make that technology suitable for all of the industrial applications. High speed, high reliability, big formulation window, being able to deal with difficult substrates really makes this technology suitable for addressing all of the different market segments. We actually have a demonstration unit at Imprint with Fujifilm Dynamics for printing decorative surfaces. We actually have our own systems for commercial print as well as supplying into other partners. Home textile, we have a number of products that are being launched at EDMA that you'll see using the reactive dispersants. And also packaging. Again, we have our own system, and also we supply ink to our partners. So we actually supply at 3 different levels into all of these markets. First one is the component where we supply the colorants, and the ink formulators can basically use that to make their own ink formulations. And also Fujifilm formulated inks. So we can also provide you with ink that can go directly into your printhead. Because of our economy of scale and very strong quality systems that we also have a very attractive package for contract manufacturing. So a lot of OEMs give us their formulation and ask us to make their ink for them. So that's the different level of supply that we can provide. And of course, being part of Fujifilm, we can also support you with systems if you are looking for actual final printers. So there is a number of levels that we basically interact with our customers. So in summary, to give you a brief introduction about Fujifilm and our heritage and where we come from, obviously we've been a long-term player in the industry for the last 2 decades. And because of the type of products and our legacy, we have an extremely high quality standards. We talked about the concept of the life of an inkjet drop and used it to highlight the benefits of the reactive dispersants, and also highlighting our position within the Fujifilm family and different levels of supply to our customers, and basically the strong position that we have within Fujifilm. So that's my presentation. I don't know if you have any questions.
Thank you very much. Are there any questions from the audience? Okay. The RDX technology, if you put it into an ink, let's say, what is the curing? Is it independent, or is it more suitable for a UV or for an IR curing process or for an aqueous system? Or is it really doesn't matter where it is applied in the end?
Yeah, so the reactive dispersants, if you formulate that into a water-based ink, you basically have to evaporate the water, obviously, so that's a drying step. The curing really comes from the binder and the latex that you add into your system. So for some of the applications, for textile, for example, you have to really understand the film formation temperature of the polymer that you're using, and that's basically your curing step. Yeah.
Thank you.
Sure.
There's one question.
Hi. What about the viscosity of an ink formulated with this kind of pigment treated with this technology compared to the self-dispersed pigment? Of course, speaking about the same formulation.
Yeah, so the concentrate at 15% or 20% actually comes in at very low viscosity. So you can take that and formulate it to very low viscosity ink as well as very high viscosity ink, anywhere from 2 centipoise all the way up to 11 or 12 centipoise. So you have no issues with viscosity from that point of view.